Well, here's a block diagram of the thing I'm showing you. So first of all, we need a high vacuum for this thing to work. We need a vacuum so that the molecules or atoms are able to freely move without restrictions. And when the atoms and molecules are able to move without any restrictions, we can measure their mass by the simple application of Newton's laws. The vacuum that I'm getting here, it's not as good as I'd like to get, but it's just about good enough for this thing to work. It's approximately 1/10 of a millionth of atmospheric pressure. It does go down to slightly better than this actually when the thing's been on for some time. Now, because we're trying to get a vacuum good enough that the molecules don't bump into each other, this causes a problem with pumping, because all the basic gas laws rely on Brownian motion of molecules bumping into each other, and when they don't bump into each other, it's very difficult to pump gas. So to get down to these sort of pressures, you can't use a normal mechanical pump. So we're using a thing called a diffusion pump. These sort of pumps work by imparting momentum to the molecules. This pump, you can look this up somewhere else if you're interested. It uses a jet of high-speed molecules that are caused by boiling a pumping fluid, and these are used a bit like a leaf blower to blow leaves about to force the gas we're pumping in a particular direction. But it does compress the gas by a very big ratio. It can compress it by 100,000 to 1 or more, and then this very rarefied gas, which is compressed to a higher pressure, can then be pumped by a mechanical pump. You see on the left hand side of the diagram there's the diffusion pump and then a two-stage mechanical pump. So when we've got this vacuum, we need to introduce a small amount of the thing to be analysed into that vacuum without destroying the vacuum, and so for this it needs a leak valve which just leaks a tiny amount of the substance into this vacuum. And this is a homemade device. I'll show you a bit more a bit later. So when we've got this substance in there, you can see down at the bottom of the vacuum chamber, the high vacuum area is all enclosed in the thick dark blue line. So down at the bottom there, the sample is ionized. This is done by having a filament which is actually just an ordinary 12 volt 20 watt lamp with the glass broken off it, which glows white hot, and the electrons are able to gain enough energy to leave the filament when it's white hot, and they're attracted away by an electric field, and these electrons moving through the area where there are the sample molecules will interact with them and knock the odd electron off, and a very small proportion of them will be left missing an electron. So these ions, charged molecules of the sample, are then extracted by using an electric field. They're moved upwards away from this ion source down at the bottom side of the chamber here. They're moved upwards and into this arrangement here where they're focused, and focused into a narrow beam moving upwards in the vacuum chamber. Now we've got a narrow beam, but we also need to align this beam with the mass filter. Here is the mass filter, and so there are two sets of deflection plates. So the first one moves them through an angle, and then the second one aligns them with the quadrupole filter. So we now ideally should have a beam which goes through the quadrupole filter. And I think some of the problems I'm having at the moment are to do with getting the ions into the quadrupole filter. So in this filter, only ions of a particular mass will be allowed through, and the ones that do get through are then filtered in the particular mass range we're looking at, and they hit a detector, and then there is a very sensitive amplifier which amplifies a tiny current which results from the charged particles hitting the detector plate. If a particle that is neutral, it doesn't have any charge, hits the detector plate, there's no current. But if a charged particle that's missing an electron hits the detector plate, then an electron will flow out of this amplifier to make up the deficit on the ion, and so the presence of these charged particles hitting the plate causes a current to flow out of this amplifier, and that's what's detected. Now, this quadrupole filter is driven with some electrical signals. It's an RF signal, radio frequency signal of about 2.2 megahertz, and also a DC voltage. You can look up how these things work. It's a bit complicated how they work. I won't explain this in detail here. We're just saying that we're driving it with an RF signal and a DC voltage. So you can see how that's done. There is a 2.2 megahertz LC oscillator in a screened box, and this goes through a couple of amplifiers that bring the power level up to about 10 or 20 watts this can generate. This goes into a resonance circuit that produces a peak voltage of about 1.5 kilovolts, and there is a modulator that can control this level from 0 up to full voltage, and some of this RF voltage is detected to produce a DC voltage, and a variable amount of this is also fed into the plates. So the mass which is allowed through this filter is controlled by controlling the RF voltage. When the voltage is down almost at 0, a mass of 1 atomic mass unit can get through, and when the mass is right up at the high voltage end, then it's tuned to somewhere in about 200 atomic mass units. Adjusting the DC proportion adjusts the resolution of the filter. You can see that this DC voltage is also fed off and goes through an HD converter and goes into the microcontroller, as does of course the detected ion signal. This is amplified and goes through a simple low pass filter and an HD converter and goes into the microcontroller. You can see that the microcontroller can also control the scan, because the way this thing works is the mass filter is scanned over the mass range we want to look at, and then the microcontroller will record for each sample where the mass filter was with this HD converter here, and what the detected ions were with this HD converter here. The way this is done is there's an integrator, and the microcontroller will control the integrator to scan over the range we're interested in. There is also there are various electrodes that have their voltages controlled by a fairly simple power supply circuit, and actually the microcontroller can switch the ion beam on and off. That's important in this application here, because actually these 12 or 20 watt bulbs I mentioned to you, they tend to get everything very hot, and so the way I've got this working is the ion source and the filaments are only switched on when the measurements are being made. Here is the leak valve. I came up with something myself. It uses 2.3mm sewing needles in a two-stage valve. So the sample goes into this tube here. That's just the two ends of the sample tube, and the first leak valve leaks this into an auxiliary vacuum, which is in this tube here at about a thousandth of atmospheric pressure, and the second leak valve leaks this lower pressure into the high vacuum, into the ionization chamber. Here you can see detail of the valve. Here is the sewing needle, which passes through a pencil eraser. The pencil eraser is clamped against this plate, and a tiny cutout on this plate makes the connection to one side of the valve, and the needle seats in a small diameter, well, a sort of capillary tube that's soldered into the back side of this plate, and that makes the other side of the valve. So this rubber, of course, isn't used for the high vacuum connection. The high vacuum connection is in the capillary tube. Here is the ion source. You can see the 12 volt 20 watt bulb here. This is a piece of nickel plate. It's all spot welded together. This is the focusing structure for focusing the ion beam, and the ion beam comes out towards the bottom of the page and goes through the alignment structure that aligns it with the mass filter. Here's another view of the ion source. You can see the tube soldered into the bottom of the leak valve plate, and the glass feed throughs here. This is the quadrupole mass filter. You can see these rods are of 4 ordinary pieces of brass rod stock. I've tried to get bits without too many blemishes on the critical inside surfaces. They're screwed together by these PTFE plates, or holes in the PTFE plates where the ion beam goes through, and these straps strap the adjacent ones together, so there are 2 electrical poles to the filter fed in antiphase. And this is the sealing ring where this straddles 2 of the vacuum T-pieces. These parts here are used to align the rods to get the correct spacing between the rods. This is the ion detector. You can see the vacuum flange here for the ion detector. This is the sealing ring. This grid screens the ion detector from the high voltage electric fields on the mass filter, and this here is the ion detector. Here is another view of it. You can see the screen box here with the amplifier in it, and this is the vacuum flange. The amplifier has got about a 10 femtoamp noise level and about a millisecond response time. This is a homemade ionization gauge for measuring the high vacuum. Here is a electron source made from a 12 volt lamp, and the electrons leave this filament and are attracted towards this spiral electrode, and this electrode down the centre collects any ions that are generated as a result of the electron stream, and the ion count is a measure of how good the vacuum is. Here is the other side of the ion gauge. Has a valve to allow air back into the chamber when it's switched off. Here is a commercial HP ionization gauge I used to calibrate the homemade one. That's working under high vacuum, of course, with the heater on. Here is the diffusion pump. This was a new old stock one I got from eBay. This is the high vacuum connection, and the jet of vapour goes in this direction from right to left and compresses the high vacuum gas that enters here down into this end of the pump, and the outlet comes out here and leaves this port here, and this of course is just a condenser to condense any vapour in the outlet. This is the heater that heats and boils the pumping fluid. This is a homemade room temperature baffle to stop the the vapour getting out of the pump. This is the other side of it. The first side I showed you bolts onto the vacuum system, and this side bolts onto the pump. This is a Peltier called cold trap for the second stage of stopping the vapour. These are the parts of the cold trap. It's actually been improved since then. This is an earlier baffle. So this is a water-cooled plate that the Peltier plate bolts inside. The water goes around here, comes out the top, goes in here. This is a vacuum connection, a backing vacuum connection to evacuate the chamber where the Peltier plate is. These collars clamp this flange into this plate, and the other parts go on top. You can see the two rings, the outer O-ring and the inner O-ring. And here is a picture of the other side of it. So the outer O-ring goes around this face here and seals against the vacuum flange and keeps the air out. This area here is the compartment the Peltier plate's in, and is at the auxiliary vacuum, about a millibar. And this O-ring here seals the inner chamber. This is the high vacuum in here. This is the drive for the Quadrupole mass filter. This is 2.2 MHz oscillator in a screened box. That drives an amplifier and modulator in here, and the amplifier feeds a resonator in this screened box here, screen to keep the RF fields in. There's a fan that blows air through this box to prevent the resonator from heating up, because it has some heat dissipating it because of the RF, and it's important it doesn't heat up because it's got a narrow bandwidth and it mustn't go off tune. This is the RF sweep of the Quadrupole drive. The dynamic range of the oscilloscope isn't good enough to show you how good the linearity really is, but you could see 3 of these sweeps. You could see the middle one and one with 10 times gain, and another one with 1/10 of the gain, and at the bottom and the top you would just start to see some compression. I think this might be the top one. I think you can possibly just see some compression there. This is a beating effect to do with the scanning of the oscilloscope and the scan of the camera the photograph was taken with. This is a thermal vacuum gauge, homemade thermal vacuum gauge. It uses a torch bulb with the glass removed, and the torch bulb has a current fed through it that keeps it at a constant temperature of about 100 degrees C, and the amount of power that's put into it to keep it at that temperature is a measure of how good the vacuum is, due to the change in conductivity through the vacuum. This is for the backing vacuum, of course. This is another one, works in a different way. This is a dual transistor. One transistor heats this center device, and the other one measures the temperature, and it's suspended on these thin wires, and this measures the auxiliary vacuum actually. This is the controller that controls the sweep. This has got the microcontroller in it that controls the sweep and the data gathering, and the integrator that produces the linear sweep is on this board. Here is the complete mass spectrometer. You can see along here the tube that the ion beam goes along. The ion beams actually go from right to left, not bottom to top as was shown on the block diagram. So here is the ion source. The ion source extends somewhere here into this T-piece, and the ion beam goes along here. The Quadrupole mass filter is in here, and then the ion detector is at the end here. You can see the vacuum system down here, the diffusion pumps down here. This is the room temperature baffle, and this is the cold trap up here behind this bracket. Up here you can see the drive for the Quadrupole filter and the RF leads coming down, and this is where the connections go through to the Quadrupole mass filter. This is looking from the other side. There's nothing very much new to see here. You can see the 2 mechanical pumps. This is the backing pump, and this is the auxiliary vacuum pump. So this goes down to below 0.1 of a millibar or torr, and this goes down to about a torr or maybe a bit below. Here is the front of the thing. This is a plus minus 12 volt supply that there's quite a bit of current taken. There's 10 amps taken by the Peltier plate and a few amps taken by the RF amplifier. This is another power supply that supplies the plus or minus 100 volts or so for the ion focusing. This little box is some of the monitoring, temperature monitoring and so on. This is the controller that controls the scan and the data acquisition. This box is the control for the thermal vacuum gauge for the backing vacuum. And there's a device here that shows the water flow rate. All these controls control the alignment of the beam, and these controls here control the vacuum systems, diffusion pump and so on. And there's a little meter here that can be switched to check various things. This is the water cooling system. The bush is quite important. It keeps the sun off what's inside the bush, and inside the bush there are 3 of these dustbins full of water and a copper tube that passes the cooling water through there. So it's largely by the thermal inertia it works, and perhaps it loses a bit of heat around the outside as well. There's not that much power. There's 250 to 300 watts that has to be dumped away, but the aim is to keep the water as cold as possible coming back to the thing, because the supply of water to the Peltier plate wants to be as cold as possible. And here are the tubes that go inside. Here's my old Drummond lathe, and here I'm making the final cut on the vacuum flange for the ion source. You notice that the hole is off centre, and so I'm using a 4-jaw chuck here. The important surface, that is the vacuum seal, is on the chuck side, and so that's protected. The plate came with a plastic coating on it on that side, and this side of the plate will be soldered to another plate that has the glass vacuum feed-throughs in it. I need to be careful that the swarf doesn't scratch the inside of the plate. It needs to be a good surface. Well, that's that cut done, so hopefully it should fit. So here is the finished vacuum flange for the ion source, and its sealing ring that seals it to a T-piece. It needs to have some other holes drilled in it, and also, as I said, it needs to be soldered to another plate which carries the vacuum feed-throughs. Well, thank you for watching. Hope you found it interesting.